markets and interesting exploration areas of AI. So when we were kind of putting the program together, and I'm a little jaded on the hype of it, a little like fatigued on the hype of it. I use it, but when Adam came around, I'm like, okay, that sounds cool. That sounds cool. We need to address it, and so kind of made our pick list for who to kind of talk about these edgy, new topics. So with that, I won't belabor it. Adam, thank you for being here, and good luck.
Thank you very much. Welcome, everybody. Timeless tech to modern magic, building multi-agent systems with finite state machines. I think it's clear to see which part of this title was generated by AI and which one was the best that I could come up with. My name is Adam Turlson, and I'm an engineer, not a marketer. So let's dive right in. What is a finite state machine? Well, it's a model that defines your system as a series of states and the transitions between those states. So before we dive into the individual parts of a state machine, I want to play a little game together. It's a game you may have heard of called rock, paper, scissors. The rules of the game are on the screen in front of you. So let's play that together. It begins by locking eyes with someone around you. Once you've locked eyes, you say, rock, paper, scissors, shoot. I almost got that. Let's play again. Best out of 3. Rock, paper, scissors, shoot. Don't play with me. All right, come on. One more time. Rock, paper, scissors, shoot. All right, that was our last round. And finally, you can admit whether you won or not. I lost. Okay, whatever. So the rules of our game are described with different parts. The first are our state definitions. When we're locking eyes, or we're selecting our throw, or we're comparing that throw. It models explicit transition logic, how we move from one state to the next. So starting our round, or when we say shoot. Those transitions can have condition logic called guards, which, for example, check whether our throws are the same, and if yes, we immediately go back in to select another throw. Otherwise, we move on to the comparing state. As we make those transitions, we can apply actions and effects which specify the side effects in our system that happen. And underpinning all of this is shared contextual data that we can use as part of any of these states or as a condition in one of those guarded transitions. So this technology goes all the way back to like 1958. Unfortunately, not 1955, which would have been way too perfect for the theme of this conference. So what is an actor then? Well, an actor was me. It was you when we performed the game together. An actor brings independence, autonomy, and communication. Actors have isolated behavior, and they interact with one another through message passing. When we're saying rock, paper, scissors, shoot, but also the throw that we make is a form of non-verbal, verbal messaging as well. In software, an actor can only do 3 things. It can send and receive messages, it can update its state as determined by its internal behavior or logic, and it can create new actors. And of course, that actor's internal state can be defined as a state machine. So all of the visualizations and all of the code that I'm going to share with you today were built using a library called XState. XState is for state management and orchestration. It allows developers to model their logic as actors and state machines. It has 0 dependencies. It handles the most complex logic you can throw at it in predictable, robust, and even visual ways, as you just saw. It's written in TypeScript, and it has about 30,000 stars on GitHub, so it's pretty popular. The great thing about XState, or one of the great things, is that it separates the what from the how, the description of our application from the specific implementation details. So the description contains things like our initial context, the available states, how you transition from one to the next, what actors we're invoking and when, the guards, what actions happen during those transitions. All of that exists on the left, but you'll note that it's only referencing these things as strings. So on the right, we have the opportunity with the setup function to define the explicit implementation details behind those strings. So for example, we can define different actors using XState helpers like from promise, from callback, from observable, and there's some others. We can define actions to emit events, send events, assign data into context, and more. And of course, we can define those guards, where we have access to both context and the event, and we can return whether or not that transition is valid. So what can you do with state machines? Well, I want to tell you more about what we did at Best Buy to build new retail transacting solutions for our customers. So when I joined Best Buy in 2020, my direction was to build new ways for customers to purchase products from our stores. Leaders wanted to improve not only the customer's experience, but the blue shirt or the employee in the store as well. The initial idea was in-aisle transacting. So imagine the blue shirt with an app on their phone, scanning the customer's products, using a Bluetooth-attached card reader to collect payment, sending a receipt via email, and then the customer can leave. So, moreover, leadership decided not only were they not going to use BestBuy.com's cart and checkout services for this, but they weren't going to use our in-store POS systems either. So we had the opportunity to essentially architect from a technical greenfield a brand new retail transacting solution. So we started with the data. At Best Buy and at many other large retailers, there's a standards-based document that defines that transaction actually took place, and it's called the retail sales POS log. So this standardized schema is defined by an organization called ARTS, and it contains hundreds, sometimes thousands of lines of XML that capture who, what, where, when, and how that transaction took place. I think it's accurate to say that from a domain-driven design perspective, this is both an aggregate root in that it encapsulates all of the validation logic for all of its child entities, like valid line items, valid forms of payment, and it's a source of truth. You know it's a source of truth because an individual POS terminal in a Best Buy store will still be able to transact when it is disconnected from the internet, disconnected from the corporate network, even disconnected from the internal store network, because it is able to generate this document and validate it against its rules engine, and when it comes back online later, it'll send that into the sales hub, which distributes that document to dozens of downstream services that produces probably millions of effects across the entire enterprise. Effects like updating the general ledger, or sending out a daily sales report to store GMs. And those POS logs are consumed in near real time. So, the challenge, however, of course, is that we cannot build this POS log within the life cycle of a single request or a single interaction with the customer. It's built over time. It's a choreographed or an orchestrated dance in order to build that vital document. If only we had a tool to orchestrate that process. Of course we do. It's called the state machine. So that's the first application that we use them for. It's called service orchestration. So here you have a centralized service that understands the whole flow, the whole picture, and is directing that next step along the way. That sequence is predefined, it's predetermined, and it's deterministic. So contrast that with choreography, where you may have your services send events into like an event hub, where other services will listen to those events in a pub-sub model to execute their part of the flow. But the great part about orchestration is that we were able to implement what is called the sagas pattern. In the Saugus pattern, you have a distributed transaction that takes place over a number of distinct steps. And if one of those future steps or later steps in the process fails, you may need to apply what are called compensating transactions in order to get the customer back or the user back into a valid state. So for example, in our process, issuing the receipt and sending the POS log comes after we collected payment from the customer. But if we fail to send that receipt for some reason, or the business fails to get its POS log, we don't want that customer to think that they can leave, and we don't want to take their money. So we need to apply the compensating transaction of reversing that payment and bringing them back into the selecting payment step with feedback so that they can retry and go through that process again. So I mentioned that we built this initially for in-aisle transacting. And you may have noticed the date. It was 2020 that we were doing this. So we started to ask ourselves questions like, will we ever stand face to face with another human again? Right? So enter one of the main benefits of state machines. They are adaptable and modular. So we quickly pivoted. We found that this very same precise process with few adaptations could be used to deliver mobile self-checkout as well. Instead of the blue shirt going through this process, it's the customer doing it themselves. And so we launched mobile self-checkout and rolled it out to more than 900 Best Buy stores. And it's available today, not that anyone knows about it. So what is our transaction orchestration service capable of? And it basically boils down to just these 7 things. So the mobile app connects to the transaction orchestration service over a WebSocket, which creates a new independent session for that user. So that's their independent state. The state machine is listening for commands, something like add item. And we don't ask that the customer pass in all of the data necessary to add that item as required by the POS log. They maybe just pass in the UPC information. We go out to GraphQL behind the scenes and various downstream services to augment that data on their behalf and update our internal context. Along the way, we're sending events back to the customer so that they have feedback on whether those downstream service calls were successful, they failed, or in addition, updates in between so they can understand the progress. As I mentioned, we're storing that context, building up that data model internally so that at the end, we can output that data model to the Sales Hub service. So squint your eyes a little bit and look at those seven capabilities of our service. Does that sound like any super hyped term these days? I'll come back to it. The next thing that we did, sorry for the blinding white, is that we built our UI itself using state machines to orchestrate the process. So, for example, you move from scanning your products to reviewing those products to selecting your payment to getting, a waiting screen and then finally a confirmation. That itself was modeled as a state machine. So along the way, in building this new architecture, I had the opportunity to get it reviewed by Bruce Odell, a personal mentor of mine, who said, I've never met a finite state machine I did not like. Now, why might someone like Bruce Odell, who's been in IT for 40 years and working as a senior principal security architect, say this? Now, of course, it's a total appeal to authority, but the reason he said it is because state machines bring significant advantages to the operator. They're predictable, they're traceable and auditable, they're reliable and recoverable. So for example, you can do what's called time travel. So let's say your current state is lost, but you have that full log of events. You can replay those events to recalculate your current state. But maybe you only replay some of those events. Now you're at a historical point in time, and you can apply new events to move forward from there. So that's called time travel. They're low latency. They're declarative with the state chart that I mentioned. They're easily tested. You can do what's called model-based testing, where you can programmatically exercise every valid transition in your state machine and be confident that you're not leaving out any edge cases. They're modular and adaptable, like I said, or like we demonstrated as we pivoted from the blue shirt-led solution to mobile self-checkout. They're scalable, both in terms of service hosting and in terms of business logic complexity, and they allow you to model those error scenarios, like with our Saga's pattern that I mentioned before. They have challenges. Maybe you're modeling a system that has hundreds, thousands, maybe infinite number of states. Well, a state machine might not be a good choice. You have to worry about transition management. So let's say you're integrating with a third-party service, and they return a response that you didn't really model as an event in your system. You may get an error that says invalid transition. Your machine doesn't do anything, but it doesn't know what to do with that event. Thankfully, that can be logged, and you can update your system. So because state machines are effectively single-threaded, where you're processing one event at a time, you take on the challenge of solving concurrency and parallelism. Now, this is where something like Azure Service Bus Sessions or AWS SQS FICO message groups would come into play. They have a lack of flexibility. You have to deploy a new version of your service in order to change your process, and then you need to worry about versioning. And they have a bit of a learning curve. I think that learning curve is a joy, but you may be experiencing something else right now. So I want to draw your attention again to this list of advantages. And I want to say that these advantages of state machines are everything that LLMs are not. LLMs are not predictable. They're not traceable. They're not reliable. They're not low latency, etc. But as an engineer, combining these two together, we have the opportunity to build a system that brings together the strengths of both of them to augment the weaknesses of the other. Fast forward to 2025, and Gartner and probably everyone else has said that the number one technology trend is agentic AI, where autonomous AI can plan and take action to achieve goals set by the user. But I think almost more importantly is that second trend that they call out, AI governance platforms. Here, technology solutions enable organizations to manage the legal, ethical, and operational performance of their AI systems. Now, I don't know that state machines have anything to say about the ethical or maybe legal aspects of building AI, but I'm confident that they have something to say about the operational performance. So it's kind of funny to go out and speak with other engineers about AI, and a common question is, well, what's your definition of an AI agent? So it's hilariously varied. So I want to try and narrow in and talk about what are the requirements to be an AI agent. And I came up with this list here. There are many others. But I think the agents must be autonomous. So they need to operate independently, making decisions and taking actions without constant human input. They need to be goal-oriented, designed to achieve specific outcomes. They need to be aware of their context, able to sense their environment and get more information to make decisions. They need to collaborate and work with others, both agents and humans. They need to be interactive, communicative, give updates. They need to have persistence to retain memory, to make better decisions over time. And finally, adapt and learn and improve with that new data. So I return again to that list of 7 things that the transaction orchestration service did. Do they look similar at all? I mean, you kind of need to, do a little mapping here. But I think that there are many parallels to be seen. We're creating sessions where that user has an independent workflow that they can go through. We're taking commands where it goes and achieves that outcome, sometimes with human input along the way, sometimes It's a long-running process that happens fully autonomously. We're augmenting data, aware of context, going out to GraphQL, get more information, go to our domain services. This is a bit like sensing the environment of a service, right? It can collaborate. It's orchestrating requests across all of those downstream services, taking the output of one, giving it as the input to the next. It's interactive. It's sending events back to the user so it knows, or they know, what is going on and receives updates. It's storing context, and of course we're finally outputting that data model, which is maybe akin to like structured outputs. But the one thing that the transaction orchestration service wasn't was adaptive. It didn't learn. It didn't improve with that new data. And that's the promise that LLMs bring to the picture. So we have our three building blocks then of agentic systems. They're the actors that provide autonomy and communication. They're the state machines that provide structure and enforce predictable behaviors. And they're the LLMs that bring dynamic intelligence. And I think this slide plays in reverse. If we remove any of these aspects, I think we cease to be building an AI agent. So with that, let's go into the agentic state machines pattern showcase, where we look at this through the lens of state charts. So the code for everything that I'm showing is out on GitHub. And if you like it, maybe give it a star, because they're the only points on the internet I care about. So, our showcase begins, just like the human race, with tool use. And I'm showing here a graph charting autonomy versus development. The challenge when building agents or talking about agents is that they're all different. They all have different capabilities. They all have different strengths. And so it can be helpful to use a dimension to distinguish between them. So here I'm choosing autonomy. How big of a goal can your agent actually tackle? Is it just doing one super tiny thing? Or is it able to accomplish a wide variety of tasks? Does it work alone or with others? So let's look at tool use. In tool use, a list of available tools is given to the LLM, and the LLM doesn't invoke that tool or method call directly itself. Instead, it returns a JSON object which describes to the caller how that method should be invoked. So then it's up to the caller to call that method, get the response, model that as a response object to the LLM that it expects, and pass it back in. So you would do this especially when you want to add additional functionality which is required by your LLM. So for example, to get more data, to send a request, to take some action, etc. And it dramatically improves the capability and response relevance. So in this example, we have a recipe writer, which is just creating a recipe, say, to make tacos. And it has an available tool called Get Inventory to check the available ingredients on hand so it can produce a recipe using exclusively those available ingredients, right? So it could just make a generic recipe, but by giving it access to more data through tool use, we can dramatically improve the response relevance. So now right away, let's talk about how we can add human in the loop. Sorry for that. So here in the state machine, I've added an intermediary step called waiting on approval. And this is where an administrator or really any actor has the opportunity to approve or deny that tool request. So why do we do this? Well, because LLMs are unreliable to begin with. But maybe your tool call is especially expensive or risky, or it takes a long time. And the wonderful thing about state machines is that it makes explicit which human you're integrating with and how they approve this process. And it could be modeled in any number of ways. So here our model wants to use a tool. It goes to the approval step. My operator denied it. It tries again. That time we accept it. We finally call the tool and pass the response back. So consider the perspective of that calling model step. It doesn't know anything about that entire process to follow. Modular. Next, feedback. So that was one agent. Now let's put that agent together with another. In feedback, one agent takes the result of another agent and gives feedback back to that first agent on how it can improve. You do this because LLMs need time to think. They can't get it perfect in just a single request, so it often takes place over time. And the end result can be dramatically improved if that iterative process happens with feedback, either from another agent or from a human. So in this example, our recipe writer agent has a critic attached, which is maybe a specialist in nutrition. And it says, hey, your recipe has too much sugar, try using honey instead. And it can update that recipe with that feedback. And of course, here I'm modeling a couple loops, so you can easily configure how many iterations you want to have with feedback. And consider that critiquing step there, that call to the agent recipe critic, could itself be a long-running process of many, many agents, humans, and traditional services that is all compiled together to give feedback to the original one. So next, collaboration, where instead of just these two agents, we want to build a whole team. So in collaboration, we break our overarching goal down to a series of very narrow tasks, and we ask each agent to specialize in that particular task. And then the parent, this parent context or machine, brings all of those outputs together to achieve whatever the goal may be. So you especially do this when you reach kind of prompt scaling limitations. You can ask an agent, or you can ask an LLM, first do this, then do that, but eventually you're going to hit a wall. Or you can say, use these tools, but it's actually not good at using something like more than 8. So what if you have a lot of tools, or you have a long process? You start to build specialist agents and put them together in a collaborative workflow. So that collaborative workflow is a predictable sequence, and it can happen in any order. Maybe it's 2 agents going back and forth, and then the next 2, and then the next 2. Here I'm showing it in an infinite loop, just really for fun, to demonstrate that state machines don't need to have a final state. This process could sit on top of your entire organization, orchestrating thousands of agents, and it just sits there forever, cycling, constantly improving. So let's watch this run in a circle. So in this example, I'm modeling delivering a meal to a customer with a recipe that was generated by a recipe writer. So it writes the recipe, it goes out and buys all the ingredients, it prepares the meal and delivers it to the customer, it gets feedback, and then publishes a report about what it learned, gives that report back to the recipe writer so that it can improve, et cetera, et cetera. All right, so we're building quickly. Next up, agentic orchestration. So instead of having a predictable path between our individual agents, what if we want to give that direction to an LLM to decide what that next state is? And that's agentic orchestration. So we have a central planning agent that can dynamically route to the next agent in the flow based on its current context. So if your workflow is highly dynamic, variable, inconsistent, if reasoning is required to determine whether your goal has actually been achieved, or you only live once, so you may as well have some fun along the way, Or if you want to have some fun, you can do it too. So for example, in this example, I'm passing all of the available agents as tools to my orchestrator, to my planner. And when it makes a tool call, the implementation is in fact just emitting an event. And when we emit that event, I build guarded statements to route to the appropriate next state. So you can see it goes from the planning agent to writing the recipe, to the planning agent, to procuring ingredients, the planning agent, to delivering the meal, etc. And then at the end, we take control back from the planning agent and have a deterministic next step of summarizing the result before we finally complete the flow. So at this point, some in the audience are thinking, holy smokes, why not just use LangGraph, Crew AI, Autogen, agentic, et cetera, Probably by the time this talk is over, there will be 3 more options out there. And the reality is that you probably should. Many of these frameworks are based on the concepts developed in state machines. I also want to add that I believe artifacts will lead the way here. So artifacts are everything you can touch, share with someone, or pass by reference. It's code, it's stories and backlogs, it's documentation and guides, it's tests, application data. All of these things are examples of artifacts. And artifacts help set direction, they build consensus, they're durable, they support iteration over time, and they promote collaboration and openness. Ultimately, it's about building trust. So let's return to that artifact, the state chart. It is a structured blueprint that defines the behavior and life cycle of an agent. It is standard, ubiquitous language to describe the behavior of that agent. It defines state definitions, transition logic, actors and effects, guards and conditions, and your contextual data that you're keeping along the way. So, standard, ubiquitous language. Well, LLMs are good at language, so who can predict what's next? Let's see how well it can interpret that language. So for testing purposes, I passed a visual depiction of that state chart. I passed an image to ChatGPT 01 and asked it, what is this for? It's a state machine diagram for a rock, paper, scissors game. What comes after the shoot event occurs? It accurately picks up on that guarded transition and says if both players choose the same throw, the machine loops back to let them choose again, otherwise it goes on to the next step. When is a winner decided? Well, your question wasn't specific enough. A round winner is decided in the beginning stage and the final winner in the end game state. So it does a remarkable good job of interpreting the state chart visually. Imagine then that we use that as a part of the feedback loop. We'll get there. So how well then do the LLMs speak it? Can they generate state charts? And that's the final pattern on our chart here. And I had to just invent a name for this because I couldn't find anything online. But I called it chartering, which I think is delightfully apt. So in chartering, the state chart itself is defined by the LLM. And the motivation here is maybe your goal is learned later. Maybe you don't know what the process is to achieve that goal. Or maybe your goal changes. You want to create a new version of yourself to define a new process that will achieve that goal instead. And the cool thing, again, about XState is it separates the what from the how. So we can give the what to the LLM to define that process and kind of be creative about what kind of actors it may want to use, what kind of effects it's going to have. And as the developer, we can still control the how, the implementation details with the setup function. So in a prior step here, I'm adding into context that state machine chart definition generated by the LLM, and injecting the definitions of my actions, actors, and guards. So to see that in action, and to talk about some of the operational implications of doing all of this, I created a demo called Red versus Blue. So who's familiar with red versus blue and like security testing terminology? Yeah, your red team is kind of like your external threat actor, and your blue team is your internal operator. So that's kind of what I'm trying to harken to here. So the red team can invoke agents, and here I have in my dropdown all of the patterns that we showed before. So let's take a look at the recipe writer, and I'm passing in initial context of what recipe I want this agent to create. So let's launch that. Now right away we see a lot. The customer just sees the result, but the operator can see everything that happened in between. I can see the initial input, I can see progress along the way, I can see log messages, the final output. Also, XState has a super cool inspector, so I could watch that process happen in real time, and I can see the list of all of the actors that are used in the system. I can generate a sequence diagram for this process, and I can actually see every single event that happened along the way. And it's super cool because you can like drill into this and see, for example, where is it? Get inventory. Here's my get inventory output. Here's all of the ingredients available in my inventory. So all of this is available to the operator. All right. Next one. So let's look at tool approval. So here, again, I have my recipe writer using that get ingredients tool, and I added that intermediary step. So here, the customer sees, please wait while I get approval, but the operator sees tool use approval required, please approve or deny. So what's deny? That's obviously garbage. All right, so it's going to go back to the writing step, and this agent is persistent. It tries again. So, okay, I'm happy now. So we can approve. All right, got approval, and we can continue in the process. Now, some of you may note that, hey, this doesn't really feel as I expected. You know, it's supposed to be like long living, have kind of like a chatty sort of interface. So we can easily update our state machine to have an initial idle state where we're waiting for the explicit input of the customer then, instead of passing it in advance. So I could say instead, write a recipe for spaghetti. All right, please wait while I get approval. We'll approve that. Got approval? All right, there's my recipe. And we can go again. Got the recipe for pizza. Okay, not bad. Build a house. So you may have noticed in my inventory, let's take a look, get inventory, messages 10, I included bricks. So I used bricks to build a house. All right, so next thing, let's look at agentic chartering. So here, I've predefined as input a copy-paste that I did off of a website, which gives you step-by-step instructions for how to remove yourself from a mailing list. I hate junk mail, so every time I get one, I investigate how to get myself off of whatever list it is. And it's impossible, by the way. So maybe I can have an agent that'll do this for me. So I found some instructions online, I prompt it with that, and then I ask it, okay, go create a process around that. So it'll generate the machine, and then using that code that I showed before, it'll invoke kind of a child actor defined with that new machine. So I have to refresh here, do a little movie magic. Don't look at the wizard behind the curtain. We'll launch it again, and this time we'll be able to see the state machine that was generated by, in this case, O1. So it's opting out of white pages, it's searching for a profile, copying the profile URL, visiting the opt-out page, listing confirm, choosing a reason. You know, it's like not perfect, but the exciting thing about AI agents is that when it's not perfect, you just add another agent. You just always add more agents. And then you can solve virtually any problem, right? So, all right, now let's imagine that we've spawned a whole bunch of these things. What is the operator supposed to do? Well, because all of these child processes are actually associated with a single root actor, you may have seen it up there before, I have a single stop button that'll go and shut down every single agent that was running. So that's what the human on-the-move experience can be like. So where is this going? Where is this chart leading us? And I think it's leading us towards emergence. So I have one more demo to share with you. No, I'm kidding. No, we're not there yet. But in emergence, maybe that whole actor is created by LLMs. It can create that whole agentic recognition. And maybe then we will finally understand what DevOps means. So is this coming soon? Probably not. But I'm convinced that if we are going to achieve something that feels like emergence, it's not going to be because we've designed an architecture modeled on the human brain. It'll be because we've found a way to make building complex agentic systems feel like building with Legos. And all the best technology, in my opinion, has this in common. Whether you're building UIs with React, or you're defining your infrastructure as code, or you're selecting services out on AWS, you have specialized components that you're composing together into broader systems that are greater than the sum of its parts. And maybe in achieving that experience, state machines will have a role to play for the next 70 years as well. Thank you very much. So I think I have some additional time if anyone would like to ask questions. If not, we can go to lunch too. So I really appreciate your feedback. Please find me in the hall, please find me online, and let me know. Thank you very much.